We're kicking off this video looking at J.J. Thomson, the discoverer of the electron, because the photoelectric effect is about electrons. J.J. Thomson was a physicist working at Cambridge University in the late 19th century, and he discovered the existence of electrons. Up until then, atoms had been assumed to be spheres without any particles inside them, and he discovered these particles that were negatively charged, that were smaller than the smallest atom, and that every atom contained these particles. And so effectively he kicked off 20th century physics, electronics, particle theory by discovering these electrons. And he did that using a piece of equipment something like this. Now, we don't need to know the details about this for this purpose. You can see here the important parts. There's a heater and there's a cathode. And this is the principle of thermionic emission. This little diagram shows you thermionic emission at work. The heater transfers energy to the cathode. So the whole purpose is to get energy from somewhere to the cathode. It can be any kind of energy. Here, we're transferring internal energy by heating. And of course, the electrons that are sitting in the cathode absorb some of that energy. That allows them to leave the surface of the cathode and they accelerate towards the anode. Thermionic emission, obviously, because it's thermal. If we want to find the energy of these photoelectrons, well, we know that we've got a potential difference between this cathode and anode. So let's suppose we have 6 volts of potential difference. And we know that the energy is V times Q. So that would be 6 times this small q. Now I'm using small q because we're talking about individual electrons. So we know it would be 6 times 1.6 times 10 to the minus 19, which is the charge on one electron. That would give you 9.6 times 10 to the minus 19 joules. And here's a problem. We don't particularly want to be dealing with numbers that are that small all the time. We'd much rather use a unit that's going to give us whole numbers so that it makes it easier to write, to type, to talk about. This is where the unit of the electron volt comes in, and it comes directly from this equation. In this scenario, the energy supplied would be 6 electron volts, because it's 6 volts times 1 electronic charge. The conversion factor is to take your energy in joules and divide it by 1.6 times 10 to the minus 19. So you're just looking at how much energy is given to 1 electron. And that energy is given by the potential difference. The official definition is 1 electron volt is the amount of kinetic energy given to 1 electron when it's accelerated across a PD of 1 volt. So if you have a PD of 2 volts, each electron gets 2 electron volts. This then is Heinrich Hertz, famous for being the unit of frequency. And he discovered the phenomenon of photoelectric emission, which of course is the emission of electrons by light. The same principle applies though. The light transfers the energy to the electrons in the cathode here. They absorb that energy, they leave the cathode and accelerate towards the anode. Now, Heinrich Hertz was an experimental physicist. He simply noted the fact that electrons were capable of leaving a cathode like this. It was J.J. Thomson who explained that it was the light that was giving the energy, but the experimental work was done by Heinrich Hertz. He didn't explain or attempt to explain his work. He might have done in the future, but unfortunately he died at 36. The next character in our saga is Max Planck, and we're going through this saga because you need to be able to talk about the history of the development of particle theory. And of course, the development of any model in science is based upon evidence. So as more people gather evidence for one idea or another, that idea becomes the forerunner. So this is Max Planck. He was studying black bodies, and a black body is a body that absorbs all electromagnetic radiation that falls on it, and when it's heated, it radiates energy as electromagnetic waves. And as we know, those waves come in a broad spectrum of wavelengths or frequencies. The electromagnetic spectrum, a very familiar thing. What Max Planck discovered was that hot objects don't, in fact, radiate a smooth, continuous range of energies. That's wave-based physics, electromagnetic waves. Instead, he found that the energies that are radiated have distinct, very, very small values. So it looks like it's continuous when in fact it isn't. He called these little packets of energy, these small amounts of energy, quanta, which of course is the plural for quantum. And what he figured out was that the energy of a quantum of radiation is proportional to its frequency. And he came up with this equation, E is equal to hf, where h is the Planck constant of 6.63 times 10 to the minus 34 joule seconds. This is a way of calculating the energy contained in any particle of light based upon its frequency. Now, particles of light, quanta of light, are usually called photons, and this was a huge deal because Newton had thought that light travelled as particles that he called corpuscles, and Young's double-slit experiment put that idea out of the minds of every physicist because that double-slit experiment demonstrated very clearly that light was a wave. You get diffraction, and diffraction is a wave property. Max Planck then comes along in 1900 and says, hold on, there are packets, they're just very, very small and we weren't able to detect them before, but light does travel as a particle. He's considered the father of quantum mechanics as a result because he was the first person to suggest this. But it was fairly niche and wasn't an idea that was taken up by a lot of people. And then, in 1905, someone put all of these ideas together. They looked at the work of Heinrich Hertz and his experiment. They looked at what J.J. Thomson had said about it being light that was releasing these electrons, and they looked at the work of Planck. Einstein was in the situation where he could and indeed had to read all of this information that came in for his job as a patent clerk. And he absorbed all of that and started to put two and two together. This is the explanation for which he won his Nobel Prize, not special or general relativity. And I'm going to use blue as an example of higher frequency light here, and red as an example of lower frequency light, just to illustrate the point. So this is Heinrich Hertz's experimental setup. We have a vacuum here, and the vacuum is only there because as the electrons leave the cathode, you don't particularly want them colliding with any other atoms. We want to see exactly how many electrons are leaving so that we can detect them via the ammeter. So they're going to travel from cathode to anode and cause a current in this circuit. Here are the results. When you shine blue light on this cathode, a current is seen on the ammeter. Photoelectric emission occurs. Nothing too startling just yet. If you increase the intensity of the blue light, you get greater current seen. That's quite interesting. The startling part comes when you start shining red light. So, if you take red light of the same intensity as the blue light that you used and you shine it on the cathode, you see nothing. No current on the ammeter. You check your circuit, you make sure all your leads are connected, etc., etc. You shine it again, you see nothing. You turn up the energy of the red light. If you're a wave theorist, that means the intensity, the brightness. So you turn it up just in case something is going wrong, and you still don't see any current. It doesn't matter what you do with that red light, no electrons will be released from the surface of this cathode. This was the big problem, and this is the solution that Einstein found. He took Planck's quantum idea and said, in fact, light is not a wave. It travels as a stream of particles that we now call photons, whose energy depends on their frequency, according to Planck's equation. When a photon strikes a metal cathode, all of its energy is transferred to a single electron. So it's one shot. If that energy is enough to get out of the metal, then the electron will get out of the metal. If it is not enough, it will not. Any spare energy left over, if the photon is a very high energy photon, any spare energy left over will be transformed into the kinetic energy of the photoelectron as it makes its way from cathode to anode. So we have our photon of light of energy hf that comes in. Some of that energy is paid to the metal, what's called the work function of the metal, and the rest of that energy is carried off as Ke for the electron. And so Einstein put this together in a very simple equation. Doesn't look very simple if you don't understand what the terms are, but there's our photon. That's the one that's coming in and landing on the cathode. This is the work function of the metal. It's how much energy the electron has to pay the metal to get out. That's a property of different metals, so different metals have different work functions. Chemists call this the ionization energy. And then any remainder is half mv squared, the kinetic energy of the photoelectron. We can rearrange this a little bit to form this. And the purpose of us doing that is because, of course, this is in the format of y equals mx plus c. Which means we can do an experiment where we change the frequency of light that is incident on a cathode, and we measure the kinetic energy of the electrons. We plot those on a line, and we should see that the gradient of that line is the Planck's constant, 6.63 times 10 to the minus 34, and the intercept will be a negative intercept, and its value will be the work function of the metal. And that's exactly what they did over and over and over again to see if they could confirm Einstein's idea. And here it is. As you can see, this data was performed by Millikan in 1916. On the y-axis is our maximum kinetic energy. That's what we said we were going to be measuring. And on the x-axis, what they have changed is the frequency of the incident light. And sure enough, we get a straight line that is going to have a negative intercept. This point here is one of the things that we are after. This is the point where HF is equal to phi. We don't have any spare energy left over for kinetic energy, so our kinetic energy is 0. And it is the absolute minimum amount of energy that an electron needs to get out of the metal. Because photon energy is proportional to frequency, we can call it the minimum frequency of light needed for electrons to leave the metal. And that's why it's called the threshold frequency. And because we know that photons with that threshold frequency will be equal to the work function, we can use that threshold frequency to find out how much the work function is. This is a cathode of sodium, so if we do a calculation of HF, put in Planck's constant, 6.63 times 10 to the minus 34, and this number that we have here for the threshold frequency, we get a value of 2.91 times 10 to the minus 19 joules, which we can turn into electron volts by dividing by 1.6 times 10 to the minus 19, and we get 1.82 electron volts. So threshold frequency and work function are a similar idea. The threshold frequency is from the perspective of the photon that lands, and the work function is from the perspective of the metal. In effect, they end up being the same amount of energy. Of course, you could extrapolate this down to the y-axis, and you would find that that value down there is the same magnitude as our work function. The development of this idea is all about how science works, how evidence is built up to support a theory or a model. The photoelectric effect was the primary piece of evidence for the particle theory of light versus the wave theory. Now, we have lots of evidence for waves. We've had over 100 years between Max Planck and Young where lots of electromagnetic radiation was diffracted, so we're pretty sure that it travels as waves. But here we have a piece of experimental evidence, and repeated many times with many different materials, that supports this idea of particles. Now, how does it do that? Well, if light were a wave, then frequency is not a factor in its energy. If frequency isn't a factor, then all frequencies would emit photoelectrons, and that is not the evidence that we have. Also, even if the work function of the metal was high, energy would accumulate over time because the electrons would continuously absorb the energy coming from this wave, and eventually they would reach the work function of the metal and they would be released, and that is not what we see. That doesn't happen. It doesn't matter how long you leave it on. If the photon energy is not enough, it will not release photoelectrons. Also with wave theory, energy and intensity are effectively the same thing. So if you increase the brightness of the light, we should get faster photoelectrons. The kinetic energy of them would be greater, because once you've overcome the work function, all spare energy would go to kinetic energy. But that is not what we see. Conversely, to support the particle theory, the energy of the incident light does indeed seem to depend on its frequency according to Max Planck's equation. If the particle theory is right, then one photon transfers its energy to one electron. It's a simple exchange, and we know that this is true because photoelectrons are immediately emitted. If the particle theory is true, then below the threshold frequency, you won't get any photoelectrons emitted from the surface of the metal. And we do see this. If the particle theory is true, then increasing the frequency will lead to greater kinetic energy in the photoelectrons emitted. And we do indeed see this, as we saw with Millikan's data. With particle theory, intensity is not related to energy. Intensity is related to energy over time. It's the number of photons you receive per second. And so, if the particle theory is true, increasing the intensity should give us higher current because we'll get more photoelectrons emitted per second. It's just that each of those will have the same kinetic energy. And that is true. That's what we see. So it is very strong evidence supporting this idea. Now you might be thinking to yourself, how do they measure the kinetic energy of these photoelectrons? You can see how they measure current, but how are they measuring the kinetic energy of individual electrons? Well, they use an experimental setup like this. I'm just going to add one thing, and that's a voltmeter across this variable supply. What you'll notice is that the positive end of this supply is facing the metal on which you're shining the electromagnetic radiation, which is different from our original photoelectric effect experiment. On that, we shone it on the cathode. And that is deliberate. So you start this with your variable power supply turned off. You shine your electromagnetic radiation on the cathode, and you note the current on your ammeter, just making sure that it's above the threshold frequency itself. We know electrons are going to come across here, be released from the surface of the metal, move across, and cause a current. When you turn on your variable supply, obviously current is going to be going from positive to negative, but electrons are actually traveling in that direction clockwise around the circuit. And they're going to be gathering on the green end of our chamber down here, repelling the incoming electrons. The idea is you turn up your supply just enough so that the energy of the electrons you're sending around the circuit exactly balances the energy of the incoming electrons. In other words, that your current drops to zero. Because we know that W is equal to V times Q, and I'm using small q here because we're talking about individual electrons, we know that the energy of those electrons that you're sending around the circuit will be equal to the reading on your voltmeter times 1.6 times 10 to the minus 19. If you wanted your energy in joules, you'd multiply your voltmeter reading by that. However, we know that energy in joules times that is electron volts. So actually, your reading on your voltmeter will give you the energy of your photoelectrons in electron volts directly. So if it says 1.5 volts, it means your photoelectrons have a kinetic energy of 1.5 electron volts. So who's right then? Is light a wave or a particle? We have lots of evidence for wave theory. We now have lots of evidence for particle theory. Is it one? Is it the other? It's both, is the short answer to this. Sometimes it behaves as a wave, sometimes it behaves as a particle. This is called wave-particle duality. When light is shone on a diffraction grating, it behaves like a wave. It diffracts, and particles do not diffract. When light is shone on a cathode, it behaves like a particle, because waves don't behave the way we've seen in the photoelectric effect. There is a lot of YouTube information that you can find about this. Richard Feynman lectures are a particularly good resource, and I'll put a link into here of some of those lectures that you can read it if you want. And I will leave you with the words of Niels Bohr, who said, "If you think you understand it, that only shows you don't know the first thing about it."